Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 22 on integration by parts.
We turn now to one of the best all-purpose methods for integration. This is the integration by parts formula. In this lesson, we'll learn what that is, why it works, and what to do if it doesn't.
Recall that our method for computing an integral as an antiderivative is to take a differentiation rule and run it in reverse. In this lesson, we'll consider the product rule. Recall, this states that d of u times v is u dv plus v du. Now, by integrating and rearranging this rule, what will we get? Well, if we integrate both sides, then on the left, taking the integral of the derivative of u times v yields, of course, u times v. On the right, we have the integral of u dv plus the integral of v du. This leads to the integration by parts formula. The integral of u dv equals u times v minus the integral of v du. Now again, as a reminder, u and v are functions of some third variable, say x, and the way that this is typically applied is that you are given one of these terms, let's say the integral of u dv, as your problem. And this is a hard integral, one that you're not sure how to evaluate. What the integration by parts formula does is gives you a hopefully easier integral in the form of the integral of v du. Let's look at this in the context of an example. Compute the integral of x e to the x dx. In order to apply the integration by parts formula, we're going to have to identify which term should be u and which should be dv. There are choices to be made. Well, let's proceed by taking a guess and seeing how it works. Let us choose as u x and as dv e to the x dx. This is going to be a pretty good choice in that when we compute du, we get something simple, dx. But when we integrate dv to get v, well, it's an integral that we can do. The integral of e to the x dx is, of course, e to the x. Now, in this case, why did we not choose a plus c, an integration constant? Well, let's see what happens when we apply the formula without that constant. The integration by parts formula says that the integral of x e to the x dx is u x times v e to the x minus the integral of v e to the x times du dx. And now you see how the formula is supposed to work. This rearrangement gives us a simpler integral to evaluate. Of course, we know that the integral of e to the x is just e to the x plus a constant. Now, I'll leave it to you to figure out why adding the single integration constant at the end suffices. We don't have to worry about it in the middle. Now, we should probably rearrange terms, simplify a little bit, to get a final answer of quantity x minus 1 times e to the x plus a constant. In this case, you should always check your answer to make sure that when you differentiate it, you get back the original integrand. For another example, compute the integral of log of x dx. In this case, the choice of u and dv is maybe not so obvious. In general, you want to keep things as simple as possible. Therefore, let u be equal to log of x, since we know how to differentiate that. dv would necessarily be dx. Thus, computing du as 1 over x dx and v as simply x, The integration by parts formula says that the integral of log of x dx is u times v, that is x log x, minus the integral of v du, that is the integral of x times 1 over x dx. Notice how that is a simpler integral, yielding x log x minus x plus a constant. Or if we simplify, x times quantity log of x minus 1. Again, you'll want to check your work to make sure that the derivative of this is in fact what we began with, is the natural log of x. For another example, compute the integral of sine of x over x dx. Well, we have a couple of choices here. Let's try letting u be equal to sine of x and dv being 1 over x dx. In this case, du would be cosine of x dx, and v would be the antiderivative of 1 over x, that is, the natural log of x. The integration by parts formula gives what? U times v, that is, log of x times sine of x, minus the integral of v, log of x, du, cosine of x dx. Well, this does not look so good. That second integral looks more difficult than the first. I think this counts as a failure. We chose our u and dv incorrectly. There's no guarantee that the integration by parts formula is ever going to work for any choice of u and dv. But let's try again. If we chose u to be 1 over x and dv to be sine of x dx, then, well, we can compute du as negative 1 over x squared dx, and we can antidifferentiate sine to get minus cosine. Applying the integration by parts formula with this choice yields what? U times v is negative cosine of x over x. Then we have to subtract the integral of v du. We get a cosine x over x squared dx. I think this again counts as a fail. That looks like a worse integral than what we started with. What does this mean? Have we chosen wrong? Is there another way to do this? Well, no. In fact, this is not an integral that has a simple representation for its antiderivative. In fact, we call the integral of sine of x over x the sine integral. It goes under the notation SI of x. It does not have a simple antiderivative. Sometimes the integration by parts method does not work for any choice of u and dv. Well, let's move on. Let's consider the integral of e to the x, sine of x. Let's let u be sine of x, dv be e to the x dx. Computing du as cosine of x dx and v as e to the x yields, by the integration by parts formula, e to the x sine of x, that's u times v, minus the integral of e to the x cosine of x dx. Well, again, this looks like one of those situations where this formula did not simplify things. However, we should not give up. Let's consider applying the method again to the integral of e to the x cosine of x dx. Let's choose our u to be cosine of x, dv to be e to the x dx. Then computing du and v, much as before, we can apply the integration by parts formula to this integral to yield u times v, that's e to the x cosine of x, minus the integral of v du, that yields a plus integral of e to the x sine of x dx. And what do we have? Oh dear, we have our original integral again, and it seems as though we are caught in a loop. This certainly seems like a failure. However, let's be careful. Let us call this integral of e to the x sine of x I. What have we computed? We have computed that this I is really e to the x sine of x minus some other integral. Let's call the integral of e to the x cosine of x j. Then what we've computed in our last attempt was that I equals e to the x sine of x minus j, and j equals e to the x cosine of x plus I. This is a system of two equations with two unknowns. Let's substitute the latter into the former. And what do we obtain? We get that I equals e to the x sine of x minus e to the x cosine of x minus I. Be careful with your signs. In this case, solving for I yields an answer. It yields 1/2 quantity e to the x sine of x minus e to the x cosine of x. So, with two applications of integration by parts, we can solve this problem. The moral is, don't quit too early. But this yields the question, how many times do we have to apply this formula in order to get an answer? Well, I have a bit of bad news for you. You don't know. There are examples where you have to apply this many times in order to get the correct answer. However, this might not be so bad. Sometimes one can obtain what is called a reduction formula. Let's look at an in-depth example. Consider the integral of x to the n cosine of x dx, where n is a positive integer. In this case, we're going to choose our u to be something that will simplify under differentiation. Let's let it be x to the n, so that dv is cosine of x dx. In this case, du becomes n times x to the n minus 1 dx, and v is, of course, sine of x. The integration by parts formula gives what? U times v, that's x to the n, sine of x, minus the integral of v du. That gives n times x to the n minus 1 times sine of x dx. Pulling out the n gives us something that is maybe a little simpler, but it's still of the form x to some power times sine of x. So let's try the general case of the integral of x to the n sine of x dx. We'll, again, apply the integration by parts formula and make the same choices as we did before, so that du is n x to the n minus 1 dx, and v is negative cosine of x. Applying integration by parts gives what? The integral of x to the n sine of x is x to the n times minus cosine of x plus the integral of n x to the n minus 1 cosine of x dx. And now we see something of the same form as what we began, but notice that the powers of x are reduced by 1. This allows us to get a reduction formula. Continuing, here is the crucial step. X to the n cosine of x dx integrates to x to the n times sine of x minus n times, well, let's see, if we take the integral that we had on the previous slide and use the second integration by parts application, we get quantity negative x to the n minus 1 cosine of x plus the integral n minus 1 times x to the n minus 2 cosine of x dx. This simplifies a little bit into a formula that looks somewhat complicated, but note, one ends with an integral of the form x to some power times cosine of x dx, where that power of x is 2 less than the original n that you began with. Likewise, if we compute the integral of x to the n sine of x and follow the algebra of substituting in the integration by parts formula that we derived on our last slide, what do we get? We get, in the end, an integral of x to the n minus 2 times sine of x dx. These final formulae are called reduction formulae. They take a difficult integral, something like x to the n cosine of x, and reduce it to a simpler integral, x to the n minus 2 cosine of x. By applying this inductively, eventually you get down to x to the 0 times cosine of x, or maybe x to the 1 times cosine of x, and these are solvable.
Integration by parts is one of the key tools for computing integrals. You're going to want to have that well practiced and memorized. But it's not the end of our techniques. In our next lesson, we'll present a technique of integration based on substitution, but tuned for trigonometric variables.